Let me introduce our speaker for the last colloquium of the current academic year. Our speaker is Daniel Soudry from the Technion, and the title of his talk is Algorithmic Bias Control in Deep Learning. So thank you very much.
Thank you, Edid. Thank you for hosting me here. It's a pleasure to talk about my work. I'll start with a general background about deep learning, what is it good for, what is it, and then I'll dive into the different topics. First, as many of you probably know, deep learning is highly successful for quite a few years. It's a the system which gives state-of-the-art results in many tasks, such as object recognition from images, classification, localization, detection, and segmentation. If you want to do it and you have enough labeled data, then you should use deep learning. Also, if you want to generate images, you can just use this. For example, this is the website. This person does not exist. You go into this website. Each time you go in, the deep network will generate an image of a face of a person which does not exist. Okay, so you can generate images. You can do various manipulations on images. You can generate text if you want to generate all kinds of long text start from some sentence. You can go, for example, into this website, and sometimes it produces intelligible, nice sentences. Of course, a lot of people now have been using also translation from one language to another using Google Translate, or speech recognition using Siri, Cortana, Alexa, or Google Now, also powered by deep learning. And there were, of course, several success stories in games and reinforcement learning, such as Atari and Go, where DeepMind, a company owned by Google, was able to get performance which is better than human performance on many Atari games, and also in Go to defeat the world champion. It was quite surprising. Okay, so there are many applications. I will not go into that, but it seems to be a very successful paradigm. So I'll try to explain a bit what is deep learning for those might not be very familiar with this, since this is a colloquium. So let's start the basic example of a multilayer neural network. This is a function which is defined recursively, which this function you give an input x. These are called sometimes the input features, the different components of the input, and then you multiply by some metrics, and you do some nonlinear operation on the vector for each component separately, usually, and then you use another matrix and another nonlinear operation, and so forth until you get to the last layer. Okay, so this is a recursive definition from the first input layer and input features. You have in the middle, you have the hidden features, and the output, you have some output features, which you want them to be similar to some desired output. Okay, so in the end, you just have some function of the output of the neural network is a function of the input and is parameterized by all the weight layers in the middle, which you can write W as a vector of all those parameters in the network, combining all those parameters from all the weight layers. So this is a basic example of a multilayer neural network. And there are many other types of neural networks. The most successful for vision applications is usually convolutional neural networks, and also recurrent neural networks, and other types of new and successful model for various applications. The kind of general theme of those models is that large models, nonlinear, and they're differentiable. So you can train them with methods which are of continuous optimization. Okay, so we'll talk about this next. How do you use those type of models? Okay, so at any point you have any questions, please stop me and raise your hand, or just cut in and ask questions. So how do we use those type of networks? So let's look at a specific, very popular usage example of supervised learning. Suppose you have some fixed training set of the inputs, xn are vectors and yn are outputs, and you want to fit the network to this training set. Okay, what do you want to do with it? For example, suppose you have a set of images. Xn are images of cats and dogs, and yn are the labels for each image. If it's a cat or a dog, it's a binary label. You say plus or minus 1, or cat or dog. So given those type, all this set of images, you have n, large n is the number of those images. We want to find a function f such that given a new image, you'll be able to correctly classify what is that in that image, a dot. Okay, so the point here is that we want to do this on unseen X. You didn't have this image in the original training set, and you want to find the label Y on the test set. Okay, so in general, you have X, you denote by X the input and Y this label. So if you have this decision boundary that you learn to separate between the cats and the dogs, you want to know what would be the what would the classification of a new example you find. Okay, so you're trying to find these decision boundaries to find the label of this new example. Okay, and you can find this function, this decision boundary using a neural network. How do you do it? So you want to adjust the parameters to find that function, which, for example, solve this classification task. For example, you can define a quadratic loss function. You want the desired output of the neural network and the network, the actual output of the neural network to be close to each other. So you give a penalty if they're far away. For example, a quadratic loss function. Another type of penalty is this called logistic loss, where you only want the sign of your prediction to be the same. So if your sign of your predictor is the same as the sign of your desired prediction, then you have a small loss. If your prediction is with a different sign, then you have a high loss. Okay, and the more you're sure on your correct prediction, your loss will go down. And if you're more wrong, you have a higher error. Okay, and so given those all those loss functions, you can just define a training loss which sum the losses on all the data points. So the loss is between the desired label and your prediction of your neural network. And you sum all the losses with either this type of losses that they show here or other types of losses on all the data points. So your goal now is to minimize this overall training loss or empiric risk. There are various names for it. So you want to find this W to minimize this loss and get a good fit to your training data. Okay, so this is kind of the usual paradigm. You can have a lot of different modifications to it, but this is the basic way. You define this training loss, and then you want to choose some training algorithm. For example, gradient descent is a very basic and useful algorithm where you update your parameters in the direction of minus the gradient. Okay, so you have some learning rate or step size parameter here, which determines how far you're going in the direction of descent, meaning minus the gradient is the direction of your maximal descent on this loss function. You can also, if you're low on memory, for example, you don't want to calculate this loss on all the data points, you can choose a subset of this data point or a single data point and calculate the loss on only of those data points and then update your parameter. This is called stochastic gradient descent or mini batch gradient, stochastic gradient descent if you have on a subset, which is not only one data point. And you can use either of those rules or modification of them to update the parameters of the neural network, starting from some initialization. Sorry. So intuitively, what you have here, just go from some initialization and you go down on the loss function until you get to a point which is lower when from where you started, and hopefully you'll be able to reduce the loss until you get good correspondence between the desired output of the network and the actual output of the network. Okay, so this is how you do the training. So there are many open questions about this type of training. For example, how do we know this even works? Why should we get a low error? Even in the training loss, why should we converge to a low error? For example, if we start from some random initialization and we go down, in the end, you might get stuck in some local minimum and not converge to the global minimum. So your error might be quite high. But it seems that in general, in many useful types of neural network and common data sets, we have this type of behavior that all the minima we converge to have a similar low value of loss, which seems to be the global minimum. Okay, it could be close to 0 in many cases. So it seems that optimization in many cases, it's not really a big issue. It could be in some other some cases you could have an optimization issue, but those problems are mostly solved in many models. So another issue you can have is, okay, so you converge to some global minima on your training set. But as I said, we don't, what we want to do in machine learning or supervised learning is get a good performance on a new data point, not necessarily from the training set. So we want to have some good global minimum, which has a good performance on a new data set, on a new training, or sorry, a new data point. What do I mean by that? For example, let's look on this set of points. You have 5 red points, and you want to fit them using a neural network. Then you can fit them using neural networks with 2-layer, 4-layer, 6-layer, 8-layer, 10-layer, 12 layers, and you fit a function to those data points, and all neural network converge quite nicely and fit exactly all those data points. So the error seems to be quite close to 0. You get perfect fit to all the red points. But in between those points, you get a very smooth interpolation between the points, and it does not depend much on the number of layers in a neural network. Okay, so it seems that a neural network has learned a nice, smooth function, which is good in some senses. Why? Because suppose now we get a new data point. Well, our intuition says that if this new data point is not too crazy, it should be close to this line, this smooth interpolation between the data points. However, there are many different solutions to this problem. You could, for example, fit a neural network using other methods, which will perfectly fit the data points, but will have very spiky, jagged form, which now if we give a new data point, it will have a high error. So the test error can be high on some solutions, but it seems that in many times we get good solutions using common practices, which do not have this issue, which is called sometimes called overfitting. For example, in polynomial fitting, if you have polynomials and you want to fit them to data points and you increase the order of the polynomial, then you get this kind of large change in the shape. Well, like this large derivatives, and it's kind of fluctuate quite widely. So now if you have a new data point here, you'll probably have a high error if you use a high order model, but not so much in the neural network. Okay, so the main puzzle here is why do we converge to this good type of local minima, which have a good generalization performance. Other types of questions are mainly about practical bottlenecks in training neural networks. Is the fact that we want to scale up those neural networks to train them fast and with not a lot of resources, such as energy and power. And we also don't want to invest a lot of human time in finding all the different knobs or hyperparameters when we train the neural network, okay? So what do we mean by hyperparameters? So hyperparameters is just a list of all kinds of parameters which we don't really know how to adjust well when we train the neural network. They have a lot of heuristics and recommendations and some theory, but essentially people play around with those hyperparameters until they get a good performance. And these are all kinds of aspects of the neural network. Some we discussed, like the loss function, the initialization, the activation function, all kinds of things we have in the training method. And together, after we adjust all those hyperparameters and you use a training method, all those hyperparameters and training method on the training set through some training algorithm, and then you get some model which you trained on the training set. And this model can now be tested on a new test set which you haven't seen and give you a test error. The problem is that all those hyperparameters can matter a lot to the performance of the trained model, specifically which minima you converge to. For example, suppose you initialize this peak of this mountain, and you can converge to a global minimum, but this global minimum can be here or here. It could be like a different type of beach. You can go to the Bat Yam beach or the Rishon LeZion beach. Okay, so one is good with corona, without corona, and going to one of the global minima or the other will depend on all of those choices or some of those choices you made here in the algorithm. Okay, so our goal is trying to control and understand what are the parameters that affect this different behavior, and as a consequence, the different performance of the trained model on the test error. Okay, so this will be very important when we want, for example, to change a model with a good performance and scale it up. We want to change it in a way so it won't degrade in performance, for example, or we want to train it in a different way to fit a different paradigm. So again, we want to find how to train it in a way which will not degrade the performance and cause it to converge to a different solution, which may have a worse performance in terms of generalization. Okay, so this was a general background. Please again stop me if you have any questions. Now I'll go into the different works relating to this topic. I'll go first to one of the more old work, which is kind of a nice result, and then we'll go to different recent results which are also related to that. And so there's like about 3 or 4 topics, depending how much we'll make. We will be able to reach, but please again stop me if you have any questions, and if you didn't understand, just wait for the next topic and it might be better. Okay, so let's get started. So our first motivation is that when you train a neural network, sometimes you observe some kind of a weird behavior. Okay, if you look at the loss function when you train the neural network, you observe that, as I said before, that okay, the training loss is going to 0, and this is causing, like, your model is fitting better and better to your training set, which is good. But if you look at the loss function on your test set, oops, sorry. If you look on the loss function on your test set, then you see this loss decreases and then start to increase again. Okay, so this is typically called overfitting. And what would you do if you're a practitioner and you see this kind of behavior? Anyone would like to suggest? If you have this type of behavior, yes?
Maybe use regularization.
Regularization. You don't want to change anything in your training method. Just a very simple thing which you don't want to add a new thing. What would you do? Like the simplest thing.
Early stop. Early
stopping, right? Meaning that you stop at the point here where the loss is the lowest, right? The minimum point. But this is a loss for classification, which is not the actual thing you care about when you want to do well on the test set. What you do care about in this type of classification task is how many examples are you correctly classifying to the correct class, cat versus dog, right? So if you look the number of examples you classify correctly, you see this error is decreasing all the time. Like it becomes more noisy here, but it seems to keep going down. And if you would stop at the time here where you have the minimum loss, that won't be optimal. It will be suboptimal, and you should actually keep training using the algorithm. So this kind of overfitting which you have in the loss is misleading, because the loss is not exactly what you want in the end. It's just a surrogate which you optimize on, because the actual loss you want to optimize is non-differentiable. And this is kind of weird. It seems like this loss works quite well because we do improve our classification loss, though it doesn't give us a good indication on when to stop. Also, another weird thing that happens is the weights or our parameters are going to infinity, they explode. Okay, so this is simple training, a stochastic gradient descent with no regularization, really vanilla training on ResNet 44 architecture. Okay, so this is kind of a puzzle in behavior which we wanted to understand. And to understand this, we tried to first use a simple model. It's a linear model called logistic regression, or which is just a linear classifier, which you train on a logistic loss. Okay, so your neural network is just a single weight vector, and this gives you a hyperplane or a line here in 2D, and you want to find the line which perfectly separate between the classes. Say, for example, here we have two classes. So you can think of this as the last layer of the neural network, and we just want to find how the optimization dynamics here are related to what we saw in the training of a neural network. So we assume the two classes are linearly separable, meaning that we are able to pass a line between them because we saw that the training loss is going to 0. So it means that you should be able to separate them correctly in the last layer after sufficient optimization. Okay, so this loss, it's called the logistic loss. It's monotonically decreasing. And we're trying to understand what's going on with this optimization. So what we see that after sufficient optimization, we converge to some separator of the two classes. But there are many different types of separators, right? There are lots of lines which can separate perfectly the two classes. So which line do we converge to? So if we use gradient descent on this logistic loss, we can show we converge to a specific solution which has the maximal margin between the two data sets. Okay, so without anyone telling the algorithm what it should converge to, it converges to a solution which is known to have good generalization properties because it separates the two classes with the highest margin. So if you have a new example, it will, like intuitively, it should be close to your original training set. So you would like to have a good margin between them. And the previous solution, for example, might have higher error around this region. So a good margin is good for generalization, and the algorithm chooses this good solution. Why this happens is because during training, once you converge to a solution which perfectly separates the data, you become more and more certain in your prediction, right? Because the loss is monotonically decreasing. So you would like to go right here and become more and more certain, meaning that your weight vector will become larger and larger. This will cause the loss to vanish on all data points, but the ones which vanish the slowest are the closest data points, which have the smallest margin, and those data points will dominate the loss, and therefore you can show, you can prove that you get the max margin solution. Okay, so specifically the weight vector will converge in direction to the max margin solution, which is W hat. Okay, the norm will go to infinity, but the direction will go to the max margin at the logarithmic rate. And this is kind of interesting, and try to see, but why do we get in the neural network training that the test loss increase? So we said our separator, our weights go to this, have this form, which is the max margin direction, time log of t, plus some residual, which is much smaller. And we have this linear weight vector, and we train this linear weight vector using gradient descent. We get this max margin on the training set. So the training set are the points which don't have a circle around them. These are the points which the algorithm see. But there are additional points which have this circle around them. Here, the orange circle or the turquoise circle. And these points are the test set. So once we converge to some solution, which is the max margin on the training set, the weights will go to infinity logarithmically. And the loss will go to 0 on all data points, except the data points which are incorrectly classified on the test set. So there are some data points which you don't see on the test set, and usually some of them are incorrectly classified, but our predictor become more and more sure of our prediction. The weight vector increases, so you become more and more sure in your prediction, and this causes the loss to increase. Here you can show it increases logarithmically or cross entropy. So specifically, let's go back to what we saw in our experiment. We saw that the test loss should increase logarithmically. The training loss is the exponent of the log, so we get like 1/t decrease in a training loss. And the norm is decreasing logarithmically, as we wrote. And the performance on the test accuracy is decreasing logarithmically, similarly to what we get in the margin, how fast it converges to the best margin. Okay, so this was kind of a neat example where you use analytical result to get some explanation of this simulation of a deep learning network. You can also extend those results to more complicated model, but will not go into this here. I'll just mention a few corollaries or some, not exactly corollaries, some implication of this result. For example, so we got the convergence to this max margin solution, which, as we said, has good properties in terms of generalization. But what happens if we change their algorithm? So there are various other types of optimization algorithm, which are known to achieve not so good performance sometimes in this type of classification task. So if you want to get state-of-the-art result in many ConsNets classification tasks, usually people use A-SGD with momentum, while, for example, Adam seems to be less popular because it decreases the performance in generalization. So it seems that if you look on Adam, you can show it in certain cases, it does not converge to the max margin, but it converges to a different solution, which can have a worse generalization. And you can prove this for certain adaptive rate methods, such as Avogadro. Okay, so this kind of might tell you that choosing your optimization method might change a lot your final performance. It's an important aspect of all the hyperparameters which you choose during training. So you should carefully control the optimization method. Another thing that is surprisingly shouldn't matter much is the weighting of the data. Okay, what do I mean by that? Suppose you are given two classes and you now give a different weight, you give a loss which is higher for the blue points or even a smaller loss to the green points. Okay, so just that, for example, a 10-to-1 ratio, the blue points matter much more. So here you have three such examples where you have 10 times more loss for the blue points or the green points. And now you start to optimize this problem. You're just trying to separate the two classes with this different weighting. And this is used many times, important sampling to reweight an existing data set to simulate a different data set. So it's kind of a method which is used in practice, but a prediction of our, kind of a prediction of what we said as if we converge to a max margin, then a max margin solution does not depend on the weighting of the different data points, only on their location. So if you just give a larger weight to different data points, or you add more points at the same data point, it will not change the max margin solution. Therefore, the final solution we converge to should be the same. And this is indeed what was observed when there were experiments with neural network on this synthetic data set. After sufficient number of training steps or epochs, you get to the same solution in the end. And this was also reproduced in other like more realistic data sets such as CFAR. So reweighting, if you don't have any regularization, just train SGD for a long time, you get the same performance, and also investigate how other things like regularization affect this behavior. Okay, so just to summarize quickly this part, we showed that using gradient descent and certain classification models without regularization, you converge to the max margin solution. And this explains the observed kind of weird overfitting training dynamics, which we see in the neural network. And we show that certain details in the training, for example, I mentioned here the optimization algorithm, but you can also talk about the loss function and the parameterization of the neural network. They do matter to the type of final solution which you get. Do you get a max margin, or do you get something else, for example? And some details don't really matter. For example, the weighting you give the data, after sufficient iterations, this will wash away and will not affect your final solution. Okay, so now we kind of started to distinguish between what kind of set of hyperparameters are affecting our final solution. Okay, any question on this part?
Why does the convergence to max margin preserve the generalization for the percent of misclassified examples?
Preserve what? Sorry, I can't hear you.
The generalization on the other metric was preserved.
The generalization on why? Sorry, I couldn't hear.
The percent of misclassified examples doesn't become overfit. It keeps going down on the test set as well.
Yeah, so but on the test set, exactly, because the margin is getting better and better, right? You converge to the max margin, then supposedly like max margin classifiers have a better generalization performance, meaning a lower generalization error. So you keep improving when you're converging in your direction to the max margin. This conversion is very slow, it's logarithmic. I'm hoping I answered the question because I didn't hear it very well.
Yeah, you answered.
Okay, thank you. Okay, please let me know if you have any more questions. If not, I'll go to the next part. Okay, so we showed that different properties are affecting the solution, type of solution which you converge to, the optimization algorithm, for example. Now let's discuss the case where we want to preserve this solution we got in a certain regime when we scale up the neural network to a larger training regime. Okay, so what do I mean by that? So we have recent results in deep learning show that if you use more and more GPUs, which are the graphical processing units used to train deep learning networks, if you increase the number of GPUs and you combine them together, you can decrease the time you need to train the neural network to a similar level of accuracy. So see, from 29 hours to 2 minutes. And now I think it's even less than a minute. You can train this. This is on a ResNet 50 ImageNet model. So it seems that parallelization is very important if you want to accelerate training and train large models in reasonable times. So now, in order to do so, all those type of work had very expensive communication between the different GPUs, so they won't have any synchronization issues. So you can quickly update all those GPU together. But a serious bottleneck for most researchers who don't have this expensive hardware is how to avoid these issues of synchronization and communication delays between the GPUs. So what is the problem with this? So just a quickly like math, what is the setup? So we said we want to optimize some loss function. Here we just assume for simplicity it's twice continuously differentiable, and we want this loss function is a sum over a per sample loss function. So these are the samples, and we want to train it now using a stochastic gradient descent, which in asynchronous manner. It's called A-SGD here for short. So now the update of the weight vector is again minus the learning rate time the gradient on some sample or mini batch of samples, a subset. And we have this delay t minus tau when we do the update. So we can using an older copy of our weight vector, and sometimes we use subsequently we use the older copy of the data we're using each time to update the parameters. This is because we're sending the parameter to some worker, say some GPU, but sometimes the update we get is delayed because of the communication delays between all the different GPUs. So this delay causes the updates of the weight vector, these parameters, to be stale, which is a problem. We want to optimize the network and get good performance. Okay, so what do I mean by that? So if we examine the problem, we see that generalization of the neural network, the performance on the test set, degrades with delay. That's the caveat if we don't change the hyperparameters. What do I mean by that? So let's look at the generalization error of the neural network. Here it's again, I think it's VGG, something on CFAR10. And we look on the steady state generalization error, or validation error specifically. We're looking on how, what is the error after many, many epochs. Okay, so here it's about 1,000 epochs. It's quite a long time. And if we look on the convergence graph, we see we converge to kind of a flat line. There's not much change going on. And we see that even after a lot of those epochs, we have a degradation in the performance if we don't change the learning rate to this value here. Okay, so here that this dashed line, A-SGD, synchronous gradient descent, this is gradient, stochastic gradient descent without delay and some learning rate. And if we want to get the same performance as the synchronous SGD, at the steady state, we need to change the learning rate to this 0.01, while originally it was much higher. Okay, originally it was 0.5. Okay, so you need to decrease it quite a lot. So now we want to understand first why this happens, why we have this degradation in generalization in the steady state, meaning even after many, many iterations on a fixed training set. So previous theoretical work on this non-convex problem examined the convergence rate of asynchronous gradient descent, but didn't look on the steady state of the solution so much. So after we understand the problem, we want to understand how to find the optimal hyperparameters. Specifically, we want to find the optimal learning rate, okay? And also additional hyperparameters which we'll add later. Okay, so we don't want to search for the new learning rate, since our goal here is to get fast training. So if we need to search for new hyperparameters each time and readjust our training, this will make training much slower. Like will be each time we have a new hyperparameters, we'll need another axis of search in all the different hyperparameters. So we want to get rid of as many hyperparameters as possible. So our hypothesis is that what we saw, the degradation in generalization, is due to a change in the minima selection of the neural network. What do we mean by that? That this was observation already in previous work for gradient descent and stochastic gradient descent, that the specific minima that are accessible or meaning stable are for gradient descent or stochastic gradient descent or any optimization algorithm are accessible only for specific hyperparameters. Okay, so if you change the hyperparameters, they might become inaccessible. What do I mean by that? For example, this basic gradient descent algorithm, we just go down in the direction of the slope. We go down, down, down until you go to this minimum point here. This is with a small learning rate. But if we take larger steps, we increase the learning rate, we have a danger that will diverge away from this minimum point and we converge to another minimum. Okay, this is because here you see, here intuitively a bit, but you can also show this formally, this minimum is too sharp. The slope is high, so the steps will going too far each time, and then you can run away from this minimum and converge to a different minimum. Okay, so this minimum is unstable, and this minimum is stable for this larger learning rate, while the small learning rate, both minimum are stable. So in general, if you look for any algorithm, not just gradient descent, and at the set of all minima of the loss function, then for certain choice of hyperparameters, for example, we have the delay in asynchronous gradient descent and some learning rate, we converge to some good minimum. For example, it's a stable, many times empirically observed to be on the threshold between stable and unstable points. And now if we change the delay, so it's some hyperparameters like the delay to 32, then this threshold between stable and unstable points is changing. So all those points become unstable. And we converge to a new stable point, which can potentially be bad, meaning it has worse performance in generalization. So what we want to do is maybe find a different learning rate so that we can shift this threshold back to its original position, so it converges to the good minimum, which have the same performance as we had before. Okay, so now we want simply, our goal is to find a way to this threshold of stability not change. Okay, that's our goal. So how to do it? We use a common stability analysis. We assume we're near some minimum. And now we examine the dynamics around this minimum. We do a linearization of the expected dynamics. And we define A as the maximum eigenvalue of the Hessian. And then what we found is that we have this equation after some analysis, which is called the characteristic equation, which the roots of this equation give us the stability of the minimum, meaning that if we look at all the roots of the neural network, then we are on the stability threshold when the maximal root is exactly on the unit circle. Okay, and we have about delay plus 1 roots. So now we can just find a condition that the maximal root is exactly on the unit circle. And this will give us an equation as a function of the learning rate, this sharpness of the of the minimum, meaning the maximal eigenvalue of the Hessian, and the delay. So you find this connection between them, which tells you how should all of them change together to remain on this threshold. And roughly, if you just do a Taylor expansion, you get that the learning rate here is roughly like 1 over the delay. Okay, so this gives us an exact relation, which now we can use to adjust hyperparameters. But before we do this, let's check if this prediction holds. So what we do here, we converge to some, we just use standard training, and then we converge to some minimum. And then we increase the delay and also change the learning rate. So if we now change the learning rate above some threshold, then what we see is that after some epoch, we run away from this minimum. These are the time it takes us to run away from, to escape the minimum and converge to some other minimum. And you see that if the learning rate is too high for a certain given delay, you just escape this minimum and go somewhere else. And if you examine the behavior of this threshold as a function of the delay, you see it exactly matches 1 over the learning rate. Okay, so we can do various simulations like that in paper and try and see and confirm our predictions, and it seems to hold quite nicely. And another thing you can do is now extend this type of analysis to other type of algorithm. For example, the other algorithm, it's called asynchronous SGD with momentum. You can add some smoothing to the gradients. It's useful in many cases without delay, but if you add this delay factor, it was observed that this momentum is quite destructive. It hurts performance. Now we did the same stability analysis for this A-SGD of momentum, and we observed that again, if you look on the 1 over the learning rate as a function of a delay, you see it's linear, meaning the learning rate is 1 over the delay. Should change it. It should change like this to maintain stability. But the problem is that when you increase the momentum, it becomes more unstable, meaning you need a smaller learning rate to be able to converge. So this kind of increased instability caused also other problems in the convergence. This is also consistent with previous observations. So looking at the equations we had, we suggested a modification, a very simple modification to the algorithm, just adding some delay here. And this changed the picture, and now we got better stability with higher momentum. Okay, so now we can supposedly now use higher learning rates. Okay, so just to conclude what we said so far, we have different hyperparameters. You need to adjust them to maintain the minimum stability, and this will help you maintain the generalization performance. And to preserve minimum stability, we said that the learning rate should change approximately like 1 over the delay and use this shifted momentum algorithm instead of momentum. So now when you test this on, for example, ImageNet, you see that if you don't have any delay, just the regular training, then you have this error. And when you introduce delay and don't change anything, the algorithm diverges. There's no convergence at all. And now if you train on a fixed budget, not for a very long time, and you tune the learning rate, you get, like we suggested it to be 1 over the delay, you get, recover the performance to be closer to the original result. And if you also add the shifted momentum, you get even closer. Okay, so there's still some gap here. The reason is that we train for a fixed amount of time, and the hyperparameters also affect the convergence rate. Okay, so now we need to understand also how, if we can change the hyperparameters or do some corrections, so to maintain also the convergence rate to be similar, if it is at all possible. But at least if you don't want to do so, you can just train for more iterations and might still be beneficial because you can now use asynchronous SGD and care less about the delay. Okay, so there's some trade-off here of how much you train versus how much delays you have. So any questions about this part? Okay, so maybe I'll talk about now the last part, which is about how to set your initialization to get good performance. What would be a good initialization? So neural networks are usually randomly initialized, meaning we have this neural network, for example, this multilayer neural network, and it's commonly suggested by many previous authors, like the Hay initialization, the Xavier initialization, that the weight should be initialized as random, independently, identically distributed numbers, and to have zero mean and some variance, which should determine in some way. Okay, so soon I'll talk about how to determine the variance. This initialization, why would you want to do this random initialization? So we'll talk about it soon, but this was the reason for that was people wanted to have some diversity in the neural network. And this have some was supposedly had some benefits to the training of the neural network. So you want to have a lot of different numbers inside the neural network and have a diversity of weights. Another thing you want to do is to choose correctly this variance of the weights. So this is done using methods generally called signal propagation, which I'll discuss now. Okay, so I'll talk about feature diversity and signal propagation, and try to understand what of this is important. Okay, so feature diversity, what do I mean by that? Why do you need this random initialization? So we have a lot of different weights. So one basic reason that was already mentioned in the first paper, backpropagation, the original training of multilayer neural networks, was that in order to break the symmetry between different features or neuron in the neural network, we should have some noise somewhere in initialization, for example, or else the neurons will stay identical throughout training. Meaning, for if you have this neuron, and both of them have exactly the same weights in the input and the output, the training dictates, like if it's completely deterministic, the training should be the same, and the weights should remain the same for these two neurons throughout training, because there's no difference between them and the equation are identical. And you want to break the symmetry so different neurons will do different things. Okay, so breaking symmetry is one reason. Another reason is because we have this random initialization, generate random features, meaning all the neurons are different from each other. There are already quite a lot of work showing that this alone is quite powerful. If you just train, for example, the last layer or something more advanced called the neural tangent kernel, you can use those random features to get pretty good performance on many tasks. So even the initialization of the neural network is a good starting point. You can already quickly train from that point and get good performance in many cases. So maybe it's a good starting point. Another more complicated thing is the recent paper about the lottery ticket hypothesis, which showed that if you use random initialization and you train the network, then you can find in retrospect good sparse subnetwork of this multilayer neural network. For example, take all the weights and just have this sparse subnetwork of the original graph. And if you now train this only subnetwork from the beginning using its original weights, you get good performance or even better performance than the original full network. Okay, so this will make training much faster and better, but to find it, you need to train the network first. So it's kind of not very useful as is, but it indicates that this random subnetwork existed in the original initialization. So they call this a lottery ticket. And they say that you need a large network with random initialization. So you'll have a lot of those lottery tickets. And one of them will be good. And then it will enable you to get good performance during training. Okay, so if you don't initialize randomly, if suppose all the weights are the same, you will not have a lot of lottery tickets. All the lottery tickets will have the same number. There's no different subnetworks of the same size. They'll all of them will be very similar to each other. So it seems that if this hypothesis is true in this pure form, then we need random initialization and feature diversity. Okay, so this is one, this is trying to explain why do we need random weights. And another thing which is an important criterion when we choose the variance of those weights, as we want to allow good signal propagation in the neural network. For example, what we want to do is to maintain the variance of the layer to be constant throughout the network. Meaning you have some input, you can think of it different ways. For example, you have some random input, and you want the variance of this random variable as it propagates through the network to remain the same. And you need to choose the variance of the weight so that a variance will not explode or go to zero. So this is one way to choose the variance, and there are more sophisticated methods which also maintain correlations between the hidden feature, all the different layers for two different inputs. Okay, so you can do something more advanced, and you can do the same analysis also for the backpropagation, the gradients going back through the network for the train. Okay, so there are these various arguments that people use to adjust the different these hyperparameters of initialization. And now there was a recent set of papers that suggested that it might be beneficial in some cases to sacrifice diversity, meaning less randomness in the network, to get better signal propagation. Okay, they showed this and were able to train very deep networks where some of the layers had identical features or some zeroed out weights, and this kind of decreased the diversity of the features in the network, but it got better signal propagation. Okay, and that got pretty good results and enabled to get very deep networks to be trained. For example, a 10,000 layer convolutional neural network without batch node, which was quite a lot. So this kind of begged the question is can you just sacrifice all of it? Maybe do you really need this diversity, this randomness in the beginning? Okay, so there's feature diversity and randomness. They're not exactly the same. There's randomness is a way kind of to generate this diversity, but do we really need this? Maybe we can take it to the extreme and design some initialization which is not diverse at all, even not random, and maybe also get good performance. So we wanted to test this. So we designed a network called the ConstNet, which is based on a wide ResNet model. It's a standard model for classification. And the main point in our initialization was we initialized most convolution layers or weight layers to be zero. Okay, so there are different layers in the network, the activations and what's something called batch normalization. But the convolution layers, the things that marked in green, we initialize them to be zero completely. And there are a few additional layers in the neural network, such as widening layers. And there we just initialized all the weights to be 1 or some constant. So it's kind of an averaging operation. So all the layers in the neural network have just a constant identical initialization. For each layer, you have some constant, usually 0, in some case 1, or some other constant at 1, just with the same constant for the entire layer. So in this case, now we wanted to look at this network training and see how it performed. So now we first train the network with random initialization just to have some baseline. And we get this reasonable performance for those type of models. And if we now train our ConstNet in a completely deterministic training regime, as we said, there is an issue of symmetry breaking. So our network will not be able to train. So what we did, we added some source of noise. It's called dropout. It's commonly used in neural network. There's a very small amount of dropout to break the symmetry during training. And we used our zero initialization, which is, again, fixed. All the layers are, in each layer, we have a constant number for all the weights in the layer. And we got very similar performance. Okay, said, okay, that's interesting. It means we don't need a lot of randomness in initialization. Let's try to decrease dropout even more. And we surprisingly got that even without any dropout, we got pretty much the same performance. That was kind of a surprise. Anyone want to guess why this happens? Yeah, that was surprising. I guess it might be, I'm not sure if it's known or not to you, but I guess it's known that there's some numerical stochasticity, when we train a neural network in the cuDNN library, some of the operations are stochastic. So you can just this very small numerical stochasticity is enough to break the symmetry and make the network train properly. And now we can also turn off the stochasticity and do computations which are completely deterministic, and then we do get a degradation in performance. So it seems that even a vanishingly amount of stochasticity is enough to break the symmetry and get good performance, which was surprising. Now we tried a bit to understand what is going on here, like why is this network even able to train? So we examined the correlation between the different rows of the weights in the filters, the different channels of the neural network, and define this forward correlation or cosine similarity between the filters for the different layers. And what we observed that no matter what was the initialization, whether it was the zero initialization or the IID initialization, which had either very high correlation, this is minus log of correlation, so 1 is 0, or very low correlation, but eventually after training, we got a very similar value of the correlation between the weight rows. So meaning that our initialization only affected the beginning of the training, but that was quickly forgotten until we got to the end of the training, okay, which is kind of interesting. So to conclude this part, so it is okay to sacrifice diversity in initialization. We couldn't really find in the constant architecture any price to pay for sacrificing diversity or randomness. Though you can construct some symmetrical initialization that will harm performance and not constant, some other things. More details about this in the paper, or you can ask me about this if you want. And even infinitesimal hardware noise can break the symmetry. Okay, so it's very, very, the symmetry breaking is very fragile. Okay, you don't need to work much to get good performance. Okay, I think I'll stop here. If you have any questions, please let me know. You did unmute.
We have time for one question. Okay, if no one's asking anything, then I'll ask something.
Okay.
So the actually, I found the last result really surprising, and I guess because it's kind of different from the way that we normally initialize things. And the question is, given your results, do you think we should initialize neural networks differently, or do you think the current practice is good? And the fact that you don't need as much randomness as we use is, it's an interesting thing to know. But at the end of the day, the amount of randomness that we're using is not hurting results at the moment. Or do you think?
Yes, it's not. I agree. That's just a direction which is not changing result. It's not a direction which is important. I agree that it opens another way to do the optimization. Maybe in the future, people will be able to find deterministic initialization which have better performance. Okay, I'm just saying this is a possible direction. I'm not saying it's necessarily a good direction. That it might be possible, I think, at least for if you have, I'm working on quantization, okay, and we're trying to find good initialization to make a quantized neural network work well. And I think maybe there it could be a good direction to try to construct this type of deterministic initialization, which will be able to get good performance, because randomness is kind of, it can cause problems in those type of networks.
So as a follow-up question,
yes.
So you basically showed the results, presumably after many epochs, and you did show that that everything converges to the same point at the end. But say after 10 or 20 epochs, is the random initialization better than the deterministic initialization? Does it not make a difference?
Yes, so if you just do a few epochs in the beginning, then yes, it's better. Don't have, okay, so yeah, I have this, I guess this graph here. So in the beginning, there is some effect, like in the first few epochs. If you do the standard training regime, in the end, you don't get any different, depending on how much noise also you add. Okay, so if you add more noise, you have less, like the percentage of dropout, it will be quicker. The difference will be smaller. Okay, so for example, with the vanishing initialization, the hardware initialization, you could have like rare cases where you don't, even after the standard budget, we don't converge to the same performance. But if you use a bit longer, then you'll always converge to the same performance. Okay, so there are some cases where, depending on your length for the training, where you have some price for this. I'm just mostly talk about the steady state solution which you get.
Thank you. Okay, so we're actually out of time. So please, whoever wants, please turn on your microphones and let's thank our speaker. And so thank you very much. And this is actually the final colloquium for this academic year. So goodbye. Thank you very much.
Thank you.